Thank you very much.
Okay, so thank you again, Stefano.
Thank you.
And we can move to the final speaker of this session, who is Hossein Sharifi from the University of Kentucky. Okay, great. And he will talk again about cardiac remodeling, like the talk of Amadeus Gebauer. And the title of his talk is Multiscale Modeling of Left Ventricular Growth under Autonomic Regulation of Baroreflex Feedback Loop. So please, the floor is yours.
Thank you very much. So first of all, I would like to check whether do you see my screen well and can you hear me?
Yes, all perfect.
Awesome. Awesome. So thank you for the introduction. I'm Hossein Sharifi, a third-year PhD candidate at the University of Kentucky. My research has been focused on multiscale modeling of LV growth, and my today's talk is entitled Multiscale Modeling of LV Growth under Autonomic Regulation of Baroreflex Feedback Loop. So starting with some background, basically the pathological cardiac hypertrophy, which has been recognized as the death cause of nearly 43,000 US residents in 2018, is described as an early adaptive response of the heart to abnormal ventricular loading. So if the underlying cause does not resolve, the prolonged hypertrophy can lead to myocardial fibrosis, systolic or diastolic dysfunction, altered calcium handling, and ultimately it can lead to irreversible growth and heart failure. So based on the outcome geometry of the heart, we can classify the cardiac hypertrophy into two categories. First, the eccentric hypertrophy, where in the cellular level, the sarcomeres deposit in series and it leads to elongation of cardiomyocytes. And in the organ level, it leads to the dilation of ventricular chamber size with a small change in the ventricular wall thickness. The second class is concentric hypertrophy, which basically sarcomeres deposit in parallel, and it leads to increase of the cardiomyocyte width in the cellular level. And in the organ level, we can see the LV wall thickness is increasing with a small change in the ventricular chamber size. So the objective of this study was to introduce a multi-scale model of cardiovascular function, which was able to simulate the cardiac hypertrophy in response to abnormal ventricular loading. So the motivation behind this study was to develop a testbed framework, which is useful for testing different hypotheses before implementing them into more sophisticated and complicated computational models of cardiac hypertrophy, like a finite element model. So this study is built upon a previously published multi-scale model of cardiovascular function named PI-MyoVen. So this original framework, which is shown here with the red rectangle here, is made of four major modules. First, we have an electrophysiology model where it derives the calcium transient within the myocardial cell. The second module is a myosin model of contraction where it simulates the contractile behavior of sarcomeres in our model. The third module is a single hemispherical ventricle where we assume a single hemisphere geometry for the left ventricle, and we assume that the half sarcomeres from the previous module are circumferentially placed around the circumference of the ventricle at the basal level. And the last module in the original framework, obviously, is a long parameter model of systemic circulation where it simulates the blood flow through multiple compartments based on the Ohm's law. So in the original work, based on a sensitivity analysis, it was shown that how the system level properties are influenced by alteration in the model parameters from different levels. For example, the model parameters in the sarcomere level or the electrophysiological parameters or circulation parameters. So in the first paper, it was concluded that end-systolic pressure volume relationship, or ESPVR, is 50% more sensitive to model parameters than any other parameters. So it was concluded that it can be targeted via multiple therapeutic strategies. So in this study, 2 new modules were added to this framework. First, a Baroreflex feedback loop module, where it essentially maintains the arterial pressure within a user-defined set point level via continuous regulation of heart rate, calcium transient, myofilament contractility, and vascular tone. So this model was essentially defined based on the sigmoidal relationship between the arterial blood pressure and the baroreceptor output signal. So at each given time step, the calculated baroreceptor output signal derives a set of ODEs that basically regulate all the controlled parameter here. In this next module, which is a unified stress-driven model of cardiac growth, based on the implemented growth law, the growth signal was being derived based on the deviation between the mechanical stimulus from its homeostatic level. So for eccentric hypertrophy, we assume the passive stress in half sarcomeres to drive the eccentric growth law, which essentially regulates the serial number of half sarcomere around the circumference of the ventricle. And for the concentric hypertrophy, we assume that the total stress in half sarcomere derives the concentric growth law, which in turn regulates the ventricular wall volume. So in this specific study, we wanted to see how our model is able to capture LV growth in response to 2 types of valvular disorder. So first, we tested aortic stenosis as an example of pressure overloading. So this huge multi-panel figure shows how we are able to monitor a various number of parameters, from cellular level parameters such as population of myosin heads on the thick filament, to the organ level parameter like ventricular chamber size or ventricular wall thickness throughout the whole simulation. So the first column here shows the model responses from the original framework. The second one, the middle column, shows how the Baroreflex module is maintaining the arterial pressure at a set point level, which is shown here with the red line, with continuous regulation of all control parameters, which are heart rate, parameters from the calcium for calculating the calcium transient, myofilament contractility, and vascular tone. And in the last column, we can see how the cardiac growth module was changed, all basically regulating the ventricular wall volume and serial number of half sarcomere to adapt to the change in the ventricular loading. So in this specific case, we induce the pressure overloading by increasing the aortic resistance in the compartmental model of circulatory system. So in response to this condition, the cardiac growth module basically predicted a significant increase in the ventricular wall thickness. However, the ventricle chamber size did not change much. It almost remained unchanged. So that's exactly the characteristic feature of concentric hypertrophy that we expect to see in response to pressure overloading. So this animation shows 10 seconds of simulation from the final steady state, and it shows how this single hemispherical ventricle, how the dimensions of a single hemispherical ventricle has been changed with respect to the baseline and systolic dimension right before perturbing the system by increasing the aortic resistance. So and also it shows how how the afterload has been increased in response to this increase in the aortic resistance, which is shown here by this blue line, which is the the blood pressure inside the ventricle. So in the next case, we tested the mitral regurgitation as an example of volume overloading. So pretty the same format of multi-panel figure here, but in this case, we perturb the steady state simulation by inducing basically a volume overloading. So we did that by allowing a portion of blood volume to move backward through the mitral valve during systole. So the growth module responded to this condition by basically increasing the ventricular chamber size with almost no change in the ventricular wall thickness. So exactly, that's the characteristic feature for the eccentric hypertrophy. It was matching with what we expected to see in response to volume overloading from our model. So again, this animation shows 10-second simulation from the final steady state, and it shows clearly how the ventricle, how the hemispherical ventricle has been dilated with respect to the baseline and diastolic dimension, which is shown with the dashed line here from the initial or original steady state right before when we perturb the system by inducing the volume overloading. So in the next case, we wanted to see whether our model is able to capture the reversal of the growth or not. So we basically repeated exactly the previous simulation. And once the dilated hypertrophy in response to mitral regurgitation was at a steady state, we started to gradually remove the volume overloading condition. So interestingly, the model, the growth module, was able to capture the reversal of growth completely back to the original steady state level. So the model was able to capture the reversal of growth as an example of, for example, surgery of mitral valve, that we expect to see how the ventricle, the left ventricle would remodel after the surgery. So in the final attempt, we wanted to see how our model with all simplified assumptions, like a single hemispherical ventricle, would be able to capture LV growth with respect to the clinical data. So to do that, we obtained clinical data for variables that represent the ventricular dimension for 3 groups of patients. So the first group was a group of control volunteer. Second one was a group of patients with aortic stenosis. And third group was a group of patients with mitral regurgitation condition. So all data were obtained with MRI. And then we plotted the model prediction for different levels of ventricular overloading against the clinical data. So this plot here shows that for the first case, which was aortic stenosis, the first column in here, as the level of pressure overloading was increasing, which shows with the cross marker or X marker in this figure, the model predicted an increase in the ventricular mass index. However, it predicted almost no change in the ventricular end diastolic and end systolic volume index, which was quite, following the same trend that we were observing in the clinical data. For the next case, which was mitral regurgitation, the model predicted as the level of, or as the severity of the volume overloading increasing, the model predicted more increase in the ventricular mass index and also more dilation in the ventricular end diastolic volume and end systolic volume. Again, it was interestingly following the same trend that we were observing in the clinical data. So in conclusion, we introduced an open source multiscale model of cardiovascular function, which was able to capture LV growth in response to any alteration in the ventricular loading, such as aortic stenosis and mitral regurgitation. The model could appropriately predict the change in the ventricular dimension compared to the clinical data from the literature. LV growth happened while the arterial pressure was maintained by Baroreflex feedback loop. And finally, the growth algorithm was able to predict the reversal of growth in response to removal of the overloading condition. So we have a documentation website for this framework in this website. So I would like to invite everyone who might be interested to take a look at this. So definitely it's a work in progress. So it's not completed, but we are getting basically there, and we work on completing the project and especially the documenting website. So at the end, I would like to thank our source of funding, my advisors and my lab mates at the University of Kentucky, and our collaborator at Michigan State University. So thank you very much, and I'll take any questions.
So thank you. So in case there are questions, as usual, feel free to open your microphone or raise your hand. And in the meanwhile, I have a quick question. You mentioned that the Baror receptor in your model acts both on the calcium transient and on the myofilament contractility. So I assume that, so you're assuming that the contractility can increase not only because of the increase of the calcium transient, but also due to some other mechanism. So I was just curious about which is this microscopic mechanism by which the contractility increases.
So if I understood your question completely, so basically the Baroreflex module was able to regulate the system in multi-scale levels. Okay, for example, it is able to change the vascular tone by changing the compliance of veins, or it can also change the myofilament contractility and calcium transient in the cellular level. Yes, increasing the calcium transient can also kind of simulate increase in the myofilament contractility, but these two are totally different, because here we are regulating some parameters that basically derives how fast the myosin heads can shift from, for example, the super relaxed state to the force generating states. So that's totally different than the amount of calcium transient that might be increased as well, that essentially can activate more binding site on the thin film. So both of them together would be a better example of regulation of the system in the cellular level to compensate for example, a drop in the arterial pressure whenever the system needs to upregulate the arterial pressure in response to any, I don't know, perturbation in the system. So I hope I did answer your question completely.
Yes, absolutely.